Uh, Thanks for the consortium have been part of the technical team now, and alas, we have managed to be heard. So you're hearing us live from Bucharest. I welcome everyone, and sorry for the delay here. This is our second webinar in the SOS Water series. My name is Michael Mügge. I work for Utima, partner within the SOS Water Project, and I'll be moderating today. So we're running slightly behind schedule, so I'll get straight to it. So today we're looking at how Earth observation technologies can transform water resource management. We look at monitoring, modeling, and the decision-making within the SOS Water framework. So the next half hour or so, we will have primarily three parts. One is we'll look at the role of EO in the monitoring water resources. We'll look at the integration of the data within our SOS framework. And ultimately, we'll look at the future directions and innovations where EO for water management will take us. So I'll introduce three renowned speakers. I'll start with Michael Brechtbühl. Michael is a remote sensing specialist at EAWAG, the Swiss Federal Institute of Aquatic Science and Technology. And here he develops Earth observation methods using satellite data, GIS, and machine learning to study inland waters, focusing on lake temperature dynamics and ice cover in the European Alps. He's then followed by Thymen Schulz, hydrologist and remote sensing expert at Future Water. So Thymen specializes in applying remote sensing, GIS and hydrological modeling, also hands-on experience, not just in Europe, but also Africa and Southeast Asia. And finally, I welcome Daniel Odermatt, head of the remote sensing group at EAWAG. And he's a geoscientist, deep experience in remote sensing of surface waters, focusing on advancing EO methods and interdisciplinary cooperation. So let's get to it. Let's begin with Michi. I hand over the floor and look forward to the role of Earth observation in monitoring water resources. Thank you.
So thank you, Mike, for the introduction. So I will start out to give a kind of an overview over Earth observation and how the data, basically the EO techniques that we use to get EO data and how we use it in monitoring of water resources. So, sorry, we have another short delay. Okay, so to give a kind of a definition of EO and the kind of data we use, so Earth observation itself is the process of gathering information about the Earth's surface, its waters and its atmosphere. This can be done in many ways. Oftentimes it's synonymous with satellite data, but it can also be, for example, a large network of ground stations that measures temperature and so on. But one of the the key tools we have in EO is satellite remote sensing, because it provides a consistent, large-scale and repeatable observation of the Earth and the water resources. And remote sensing itself basically just means measuring something from a distance. And it has its history goes back quite a while, around 150 years, where people used to strap cameras to balloons and even pigeons, as you can see here. And then it was mostly applied in military use. But nowadays we have these large satellite constellations, such as the Copernicus Sentinel ecosystem, which supports water monitoring and global goals, such as the Sustainable Development Goal 6, clean water and sanitation. On the right-hand side, you can see an example of what we can get out of Earth observation data. So this is an example from the JRC water mapping layers, a product that uses the Landsat archive from NASA and USGS, and it basically maps water occurrence and water seasonality, and this is used for freshwater ecosystems in SDG 6.61. So to understand how these satellites work and capture data, we first have to look at a very important part of it, the satellite orbit. So most of the EO satellites that we use for water resources applications are in near polar, sun-synchronous, low Earth orbit. And this basically means near polar, the orbital plane goes through both poles. Sun-synchronous, the strip that it records is aligned with the terminator line, so the night and day line that moves across the Earth. So we have overflights at the same local time each day. So for example, for Landsat, we have measurements at around 10 a.m. in the morning for each place on the Earth. And then low Earth orbits, the most satellites we use are at around 700 kilometer altitude. And this just is in the sweet spot that we are close enough to make high resolution measurements, but measure the Earth's surface at a high frequency as well. And here you can see a schematic figure of how that looks like. So basically the satellite moves down the track and records a swath. And this swath, basically this strip it records, is then divided into scenes that we get as data from the satellite. And here you can see an example from the Sentinel-2 constellation. This is basically two satellites in orbit with 180-degree offset, so it covers the Earth more quickly. And together, these two satellites monitor the Earth's surface in about 5 days. They have the total surface of the Earth mapped. So if you go to a given spot, then every 5 days, you basically receive data from the satellites. So to go a bit more in depth in what kind of techniques that are actually used. So like I mentioned, we use satellite platforms mostly, and these use very different types of techniques to do the actual measurements. But most of these techniques are associated or are some sort of measurement of light, basically electromagnetic radiation. And probably the most typical type you will most likely have seen before is using the optical sensors. So sensors that work in the visual spectrum around 500 nanometers. And here you have an example from Sentinel-2, which is just an RGB. So the satellite records basically in red, green, and blue wavelengths, and then displays this as an image that we can quite easily understand. And so these types of measurements are often used to map turbidity. So we can measure the turbidity of waters, and this is directly linked to the suspended sediment load that's inside the waters. But they can also be used to monitor algal activity. So we can measure concentrations such as chlorophyll A that's inside the water. And then if we move further up in wavelength and further down in frequency, we go to around 10 micrometers, which is the thermal infrared range. Here, for example, we have an example from Landsat 9, which has the tear sensor. And we can basically, so whereas in optical sensors, we measure the reflected light from the sun, here we actually measure the thermal emission from the Earth's surface. And so this is quite easily interpretable as well. So you can see red is basically a high heat signature and blue is a low heat signature. And we can use this to directly measure, for example, water temperature. But it's also useful for a lot of other things. For example, we can measure land surface temperature that goes directly into evapotranspiration formulas. And then if we go even higher up at around 5 centimeters, we have a the microwave range in the electromagnetic spectrum. And here we can also passively measure the emissivity or basically the signature of the Earth, but most often these satellites actually use an active systems where they shoot down microwave radiation and they measure the backscatter from the from the returning light. Here you can see an example from Sentinel-1, which is a sensor often used with this type of technique. And this is also a quite valuable technique because we can have this very nice distinction between water surfaces and non-water surfaces. So it's often used, for example, for flood mapping, but it also is very reactive to soil moisture, so the content of water in the soil. And this is also one of its applications. And then there's also a lot of different techniques that are indirectly associated to the electromagnetic spectrum or not at all. So for example, in altimetry, we can measure the height of the water level, basically using either lasers or, for example, also microwaves with newer technologies. And then, for example, with gravimetry, we measure the gravimetric anomaly, which can be directly related to the terrestrial water storage change. So these are just some of the most used techniques that we can use to monitor water resources from EO sensors. And so to use this data, there's basically three very important aspects of resolution we have to understand. So first, we have the spatial resolution. We can have basically larger pixels in the coarser image. So this means how much detail we can see in the picture. Then we have the temporal resolution. Basically, how often do we get an updated picture of the same place or a data point in our time series? And then finally, the spectral resolution. So before I showed this example of an RGB image. So this is just a measurement in 3 bands, but newer satellites often measure a very high range of different wavelengths. And then we can even go up to hyperspectral, where we have extremely fine detail in the wavelengths captured. So spectral resolution is mainly a technical limitation, and this is improving with newer missions. But for spatial and temporal resolution, we have we still have the technical limitations, but we also have a trade-off. Because if you think about the orbits I showed you before, we can basically increase the swath size, so but this means basically we get a better coverage or a higher temporal frequency, so a better temporal resolution. But this also means that we have coarser pixels, just due to the limitations the sensors are built up. So to illustrate how important this resolution aspect is, here is an example of lake ice. So you can see basically we have a lake ice dynamic of a lake with 0% being no ice and 100% being full ice coverage. And if we start from the left with the low temporal coverage to the right with the high one, then you can see that the signal, for example, the first signal we get with the low resolution sensor doesn't even cover the full ice coverage of the lake. And so it's very important that the data sets and the remote sensing or the EO data we use has a spatial resolution that matches the observed objects and phenomena. Because if it doesn't, then we have an extremely high period of uncertainty, for example, in the lake ice measurement. And so one way we use this, we use this in the SOS-Water Project. So one of the prototypes we developed or improved on is lake ice monitoring in the European Alps. So here we have relatively small lakes that we need to monitor with high spatial resolution sensors. So here again, we have this limitation of low temporal frequency or very not so dense monitoring, basically. And one way to get around this is to do sensor fusion, so to merge different sensor platforms, but also techniques. So in this case, we use Sentinel-1 CSAR microwave, basically, backscatter, basically, and then Sentinel-2 in the optical range, and then the Landsats in the optical and also in the thermal range. So we combine 3 different techniques and multiple different platforms to get a much more dense measurement. And so in this case, we basically get the data pre-processed and have a machine learning classification framework that uses ground measurements from webcam data to reference and label the data and do the training and validation. And what we get out is an extremely dense time series of lake ice coverage from alpine lakes. And this is quite relevant because with GCOS, the Global Climate Observation System, we have defined that lake ice cover is an essential climate variable, so it's crucial to measure lake ice cover for to understand the Earth's climate. It's also very relevant for water quality because ice stabilizes the mixing in lakes and also has an impact on the oxygen availability. And with this improved monitoring approach, we can get down to 2.5 days revisit at 20 meters. So we enable reliable seasonal tracking in alpine lakes. And then before I hand over to Timon, so just a way, basically to show you a way we use this aspect of resolution in the project, in the SOS-Water Project. So our main focus in the project is to improve EO data sets and also facilitate the use of EO data for our partners in the project. So our initial task was to create a data inventory with key data sets that are relevant for the project. And we basically listed all these data sets and then also extracted or defined the attributes associated with it. So spatial resolution, temporal resolution, radiometric resolution, and so on. And this was very important because this allowed us to, together with the EO data needs of our partners, to find opportunities for new development efforts. So basically, where we could use our time to improve existing data sets or create new data sets. And here you can just see a list of the opportunities we defined in this first task. And two of them we will later introduce to you. Basically, Earth observation prototypes that we integrated into this project. Yeah, so I like now to hand over to Timon.
Thank you, Michi, for introducing Earth observation for water resources management. I will now continue with the webinar. Where do I have to push? So, Michi introduced Earth observation for water resources, but I will continue with an important question. Why should we use Earth observation for water resources management? And what are the advantages of Earth observation over traditional monitoring methods? Well, the first one is a bit obvious because there's already a lot of data available. At present, there are about 900 active Earth observation satellites in orbit around the Earth, and most of them are commercial, but many of them are also producing data for the public. And for these public satellites, the data is all freely available and covers most of the globe. And these data sets are organized in platforms such as the Copernicus Data Store, the NASA Store, and the Google Earth Engine, where you can download and modify this data. There are also platforms available that already integrate the Earth observation data and give you some processing capabilities, such as EarthMap, where you don't need any coding knowledge to get to this data. Secondly, it's a reliable source of data when ground monitoring systems do not exist or are not in the public domain. In many parts of the Earth, people are measuring by hand and data is transferred, not always transferred. Earth observation gives you the opportunity to go from a point scale to field scale or country scale and measure what you want to measure with one sensor instead of a full network. Thirdly, with Earth observation, you can quantify flows that are normally difficult to measure or are very local. For instance, evapotranspiration. Of course, you can measure evapotranspiration with the flux tower. However, this is very expensive, and this is also a very local measurement, and it varies a lot in space, so it's highly heterogeneous. Using Earth observation tools, you can monitor large swaths of and extrapolate these point measurements to field or basin scale. Here on the right side, we see an image of how Earth observation is used to estimate evapotranspiration from crops in the fields. Another important point is that it offers spatio-temporally consistent data. If you are working with gauges in the field, these all have to be calibrated, and different calibration and different locations all give bias to the data you're observing. So the nice thing of using satellites or Earth observation is that, well, you have a consistent measurement over a long period of time. This way you get rid of a lot of initial bias of the measurements. Also, it's quite cost effective. I've already mentioned that that a lot of data is freely available and in the public domain. So it's the benefits are very high and the costs are not too high. It also enables you to investigate remote regions. One example I will show you later is how we've used Earth observation to model snow in the upper Danube in places which are difficult to reach to. Another example could be that to detect illegal mining activities in remote areas. For instance, in the picture see on the left, where radar was used to detect mining activities. But how suitable is Earth observation for the different components of the water resources system? So on the right side, you see a simple schematic representing the different components of a water resources system with inflows, think of precipitation or surface water, and outflows, think of actual evapotranspiration or also surface water. And in between, we have some dynamics related to the water usage, the demands, and the table shows you how suitable Earth observation is for quantifying or monitoring the different components of the water resources system. And you can see there's quite some changes and differences between the water resources components. For instance, precipitation and evapotranspiration are more easily or less complex to observe compared to sectoral demands. And the most complicated part of the sectoral demands are mainly the industrial and domestic demands. And also one nice thing to note here is that with Earth observation alone, it's already possible to create a preliminary water balance. So for your studies on water resources management, even alone with Earth observation data, you can already find some bottlenecks or trends which you can strengthen with in situ observations or modeling. Now we're going to the second part of this webinar, in which we're going to present the integration of the Earth observation data in the SOS-Water framework. First, we'll introduce how we incorporated this, and we'll talk a bit about the case studies. And then both me and Michi will present one of the Earth observation prototypes we've developed. So Earth observation within the SOS-Water Project. So one of the main aims of this project is, of course, to define the safe operation space for water resources in a variety of case study areas. And to do this, the team members set out to simulate the water resources system in a lot of parts of the earth. On the image you see, for instance, well, the Rhine-Meuse Delta, the Upper Danube, the Mekong Delta, and the Gukar. And from the Earth observation side, work package 3 was asked to develop Earth observation prototypes to help with the Earth observation data needs for these case studies. And there are 4 ways in which Earth observation data was used to support the case studies. And the first one is as model inputs. For instance, discharge simulations, benchmarking, we're comparing modeled outputs with observed Earth observation data to fill in data gaps, for instance, for time series of precipitation inputs and indicator assessments. And this graph table shows you the different Earth observation prototypes that are developed within the SOS-Water Project. We've done our best to cover a wide range of Earth observation technologies, from thermal remote sensing to optical, using radar altimetry for Earth observation prototype 3, and also to try to touch upon different important topics like agriculture for the crop water productivity mapper and the cryosphere with Earth observation prototype 6. And these were then applied in 4 different case studies, and we'll now present 2 of them. So, well, snow water equivalents. I will present now the Earth observation prototype 6. It's on downscaling snow water equivalent. And snow water equivalent is a very complex variable, and it remains very difficult to quantify. And it's mainly due to its high spatial, vertical, as well as horizontal heterogeneity. So snow water equivalent varies a lot in space, and it's also, of course, a dynamic value variable with compaction occurring, melting occurring, and different layers having different densities. So because of this complexity, you cannot hardly use global snow water equivalent products for your benchmarking. And also the spatial resolution of these global snow water equivalent products also inhibit the use, and they most of the time lack this resolution for the local snow processes. Here on the right side, you see the grid of the Era 5 land snow water equivalent products over the Alps. And you can see that even within a pixel, there can be a mountaintop and a valley. So this data, there's some scaling issues here. So that's why this Earth observation prototype 6 has developed a machine learning based prototype to downscale this data to be used as benchmarking for the snow simulations in CWAT-M and PCR-GLOB. For this, we've used extreme gradient boosting algorithm, and this is a tree-based machine learning algorithm that uses trees to regress. And we fed the algorithm with a lot of different Earth observation covariates, originating from the MODIS satellite, climate reanalysis from Era 5 land, and the shuttle radar topography mission. And after some data pre-processing, cloud masking, we split the data into 3 data sets based on stations, 20% test, 20% evaluation and 6% train data set. And we performed a k-fold cross-validation procedure to tune the hyperparameters and select the most important features. And we've trained the model using 383 time series of measured snow water equivalent over a period of 20 years. And on the right side, you see the variable importance plot that ranks the features that are used as predictors in terms of importance. So we see that, for instance, the ERA 5 land snow water equivalent has a very high contribution, NDVI and snow class and slope and so on. So the case study of the area of the case study is the Upper Danube. Here the model was trained on this 383 measurement stations. Then a snow water equivalent data set was generated. And after that, we're also generating a snow water equivalent data set for the Rhine News to help benchmarking a PCR glob water balance model together with Utrecht University. And here are some results of the Earth observation prototype. This slide shows you the spatial distribution of snow water equivalent over the Upper Danube. On the left hand, you see the original native 9-kilometer resolution snow water equivalent data. And on the right side, the downscaled data with a resolution of 500 meters. And we see very well that the ERA 5 land data has a much higher values compared to the right side. And well, we see now also the valleys clearly. And we see that it's indeed much higher on the left side. And when we compare it also with observations, then we see indeed also that the ERA 5 land snow water equivalent overestimates snow water equivalent significantly in the Upper Danube. The red line resembles that, and the blue line resembles the extreme gradient boosting predictions. And we see that it much better represents the dynamics of the snow stations. The R squared of the extreme gradient boosting is about 0.85 compared to 0.69 for the ERA 5 land snow water equivalent. However, so on the left plot shows you that, well, in general terms, the algorithm is very good to produce snow water equivalent on average, on a basin average. But if you look on the right side, here we show the observed versus predicted station-based R squared drops. So for specific locations, the Earth observation prototype performs less strong. So the next step will be to generate this observation-based snow water equivalent data set and to, well, use it within CWAT-M to compare and calibrate the snow module. Same applies to PCR glob with the Rhine News, and this will happen in the coming few months. And now I will give the floor to Daniel. Michi again.
And yeah, so I like to present a second prototype we developed as part of the SOS-Water Project. So this is a surface water temperature mapper. Surface water temperature is a key water quality and ecosystem health indicator. As you can imagine, the higher water temperature means that habitat suitability goes down, and it can also increase algal activity, such as basically or produce algal blooms. And if you look at the Rhine River, temperature measured at ground stations in Basel have risen by more than 2 degrees since the 1960s. And recent studies also show that a further rise from 2.9 to 4.2 degrees is expected by the end of the century. So quite a high increase in water temperature. And so here with EO, we have basically hindsight. We can look back into the history of the water temperature, or we can do real-time monitoring. But in the SOS-Water Project, we mostly work with this large pathways and scenarios, so we need to do projections. So what we do here is actually do also a benchmarking, specifically of the DINWAT simulations, so water temperature simulations that come out from the modeling side. And so for our prototype, basically we use Landsat data, so data from the sensors from NASA and USGS. We use 5 different platforms. We do some harmonization, some cloud and water masking, and some a pure pixel selection algorithm that we are sure that we only select entire pixels consisting of water. Then what we get out is basically a spatial temporal time series, so maps over time. We can do a sampling of these and compare these to in situ measurements for an accuracy assessment, basically a validation of our model. And then we can also do an aggregation, so we can aggregate the data to river segments or to lakes to specify, for example, lake surface water temperature. And yeah, we set up this model, and here you can see the validation with 5 ground stations from the Rhine River main stem. And as you can see, we have around 2,600 matchups, quite a good agreement in the linear regression, and a mean absolute error of around 1.1 degree. So yeah, so basically we have set up the model, and now we can use it to do the benchmarking. So we have to somehow compare simulations to satellite observations. And so we have these daily satellite maps, and we somehow have to compare it with a high resolution of 30 meters to the coarse 1 kilometer resolutions of the simulation. And how we do this is we use the SOS-Water database, basically a database of river reaches that has been developed for the NASA SWOT mission. And we do a spatial aggregation on these river segments. Then we can do a matchup. So basically for each segment, we have a timestamp and an error associated with it. And we can use this in our analysis and do the benchmarking. And here is an example of how this looks like. So basically the simulations are using different global climate models and also different scenarios. So here you can see for one scenario, the matchup with the historical, so the data that was generated using real world data, and then with the projected data. And as you can see, the matchups are quite good. They're in agreement, but we also can see where they deviate from the measurements from the satellite. And we can also do, because we have these areas across each river segments and also across time, we can do nice things such as look at the seasonal residual. And here we can, for example, we can find that during specific seasons, the projections of the model data have a larger error. For example, here in early summer. So yeah, the next step will be to provide this data to the modelers, and then we have to look how we can improve existing thermal simulations. And now I would like to hand over to Dani.
Thank you, Michi. I will complete this webinar with an outlook on future directions and trends in Earth observation that could serve water management. In this part, I will quickly discuss a few buzzwords such as commercial constellations, digital twins, machine learning, and global collaboration. But starting with the satellite infrastructure, and nowadays the Copernicus program is the world's leading Earth observation program. So we depend largely on satellite missions comprised within Copernicus. In this scheme, you can see how we are at 2025 now, a period in which most Sentinels, Sentinel-1 to 3, move from the A-B satellites to the C-D satellites. So Sentinel-2C, for example, was launched. Sentinel-2A is still operational, but slowly being decommissioned. Which means we have the second set of satellites, but they're still sharing the same specifications like the initial ones. And then from 2030 on, we have a new generation of Sentinel-1, 2, 3 satellites, which will then have significantly improved specifications. In the period between 2025 and 2030, we have continuity of Sentinel-1 to 3, but there's also a bunch of new satellite missions from Copernicus, such as the land surface temperature mission, which fills an important gap in Europe's Earth observation portfolio, which did not have high-resolution temperature data, such as from Landsat until now. Then there is the Copernicus hyperspectral imaging mission, CHIME, which will provide the first operational global hyperspectral data. And a few more missions for anthropogenic CO2 monitoring, for example. Other missions focus on biomass, salinity, sea ice, snow depth. None of them is specifically for hydrological applications. But I think with Sentinel-1 to 3 next generation, that will have significantly improved spectral, radiometric, and spatial resolutions, we can then expect a significant move forward from 2030 on. Another addition, an important addition to the satellite infrastructure, are commercial constellations. I here listed a couple of examples of hyperspectral constellations. Similar constellations are pushed in the field of thermal observation, for example. Also, radar satellites are increasingly made available from commercial companies. In hyperspectral sensing, Planet, a large and long-standing company, is leading the field with its Tanager satellites that has specifications as shown as the right that are quite similar to those by Prisma and NMAP, for example, two hyperspectral, experimental hyperspectral satellites by the Italian and German space agency. Then there are some new candidates like Pixel that you perhaps have seen advertised, Explore, Hypersat. Many of them are part of an effort to try to commercialize the Earth observation sector. They often come with very, very promising specifications. But as, for example, is the case of the Fireflies, their 5-meter resolution means a tremendous improvement compared, for example, to the 30 meters resolution of the Planet Tanager. So when you square the 2 meters to come up with the area covered by each pixel, it's a huge advancement, and it's not quite clear if these such ambitious specifications can be met. So in summary, I think what commercial constellations will add is mostly temporal revisit time, because they will provide additional satellites that probably have similar configurations as existing ones. Whether they can push the quality of data significantly remains to be seen. In terms of methodology or the uptake of data, an important flagship initiative in the European Union is Destiny, and we've seen a lot of digital twins like applications. There was a session at the European Space Agency's largest conference this summer, where about half of these digital twin applications came from hydrology or cryosphere related to hydrology monitoring. So these digital twins as a bucket, I would say, for applications are very, very inviting for water management, because we have rather good control of models. Also, the integration with observations, with Earth observation, is rather far advanced. So the potential to meet the demand of digital twins from hydrological applications, I think, is very big. Here, as an example, I want to quickly feature an example provided by Timon from Future Water. where they have used data acquired by the SWOT satellite, which is also a rather new and very promising satellite mission for hydrological applications. This data is used as model calculations together with weather forecasts and water availability and demand estimates. They can then create forecasts, which is shown nicely here for the Pequemos Libombos reservoir. The time series on the bottom right shows a very large forecast over a few years. On the left, you can see from the dashboard how individual reservoirs' water levels are provided. And by using each SWOT observation as initial condition here, this data can be continuously updated and hence serve like a digital twin of the reservoir, the connected reservoirs, as long as it provides water level estimates for the rivers, which are too small in this catchment. Then another big trend, of course, are foundation models. We've seen in the past 2 years, Earth observation foundation models from almost every big IT corporation, from Microsoft, from Google. This one shown here was created by Esri. So the idea is that you create big foundation models trained on a variety of Earth observation data. Here shown high-resolution optical imagery, multispectral, hyperspectral and SAR imagery. You create a foundation model that can then be further trained to serve very different application cases as shown on the right. So this very fast increase of the availability of these models has not been exploited thoroughly. So there are a lot of models that have demonstrated use in certain cases, but there's no comparison of what approach or what specific foundation model works best. Also, the number of use cases where a user really says this foundation model has served my use case best are still lacking, and I think we will see a lot more of this exploitation in the next years. One general limitation that we observed with machine learning algorithms is that it depends very strongly on measurements from the ground. In this study here, we compared a number of different neural networks, which are showed by the different colors, bars. And then you see groups of color bars that represent different water quality variables. So phytoplankton absorption, organic matter, and non-algal particles. And in the situation on the left, we used a random split validation. So the distribution is the same as in the training and in the test data. And in these situations, machine learning algorithms consistently perform very well for all parameters apart CDOM at 675 nanometers. But as soon as we change the distribution of the training and the validation data a little, in the center, we still have the same coverage, the same range, but slightly different distributions. Then the performance already suffers a little. And as soon as we move out of distribution, that means if the combination of variables changes from the one in the training data, then we see significant drops in the performance. And this, I think, emphasizes how important it is to know the distribution of variables in a test site before applying machine learning models. Finally, I want to mention one of the major risks at the moment, which is the global collaboration that has always been a very strong element in Earth observation. One of the entities in charge of this collaboration is the Group on Earth Observations, GEO, which is an intergovernmental body coordinating the use of Earth observation, also ensuring the provision of Earth observation services to the global south, for example. And initiatives like GEO were very strongly carried by American funding in the past. Here, as an example, I showed the even increasing funding of the US in the past 3 years. It makes up about 40% of GEO's budget. The European Union provides slightly less. China provides about 20% of these amounts. So if you imagine that this share provided by the US is dropping in the near future, then I think these initiatives are at severe risks. There are other such bodies like the Committee on Earth Observation that coordinates, for example, the development of different satellite missions around the globe. And for those equally, I think the perspectives in the future are rather frightening. So I think there will be necessary mitigation efforts to make sure that we can still maintain a high level of collaboration. With these remarks, I would like to complete the webinar, and I thank you for your attention in the names also of my colleagues, Timon and Michael.
Thank you very much indeed, and sorry for slightly running over. We're happy to take one or two questions to slot in, and I see we have a question here. Okay, if we could share the code to downscale EO data. Simon.
Yes, there is already a first version available on GitHub, but the newly updated version will also be published on the Future Water GitHub. So yes, the answer is yes. We can share the code.
Thank you for that. And then in the matter of time, I just kind of wanted to pose a final question to the three of you, and you may answer part of it or all of it. So I was looking really, I think it was fascinating of the developments of this and where this potentially can come and bring us to. So I wanted to see how the future, the challenges with integrating the EO into hydrological and ecological models, how do we ensure that they remain relevant? And if we look ahead 10 years, what role do you envisage EO playing in ensuring that Europe remains within the safe operating space for water? And the question is open to all three of you. Go ahead, guys.
Well, I can start, and I would like to repeat what I said before with the emphasis on ground measurements. So I think the success of Copernicus in the past years was mostly based on Earth observation technology, but the progress in coordinating efforts taken on the ground for environmental monitoring and the Earth observation efforts have not been coordinated enough. For example, there is no correspondence between the parameters that are measured, between the timing at which they are measured, and the activities from space and performed on the ground still remain rather disconnected. And I think this coordination has to improve a lot, which will support activities like the digital twin development, for example. And I think by pushing this integration, Europe will easily maintain based on the satellite infrastructure that is really extraordinary. It's leading place.
Thank you, Danny.
Yeah, maybe one thing to add. Especially so in such large or in such projects as SOS-Water, where we rely on these projections to look into the future and decide whether we are doing the right things today. I think the main role that EO can do here is to have a consistent monitoring. So basically, we can rely on these projected models, but we also have to do benchmarking and see whether they're today and also in a year still aligned with the measurements we do from satellites or from other stations. Yeah.
Thank you, Vicky. Then if there's no further questions from the audience, then I'd like to again thank everybody for participating and thank our speakers again for these most interesting presentations. Stay in touch, stay informed, go to our website. And on behalf of everybody at SOS Water, Thank you very much for joining us today and wish you a great day. Thank you. Bye-bye.